Good afternoon. I'm Jim Johnston, Chief Technology Officer here at McElroy Manufacturing. I'm going to talk to you today about joining heavy wall pipe. I will cover some industry best practices related to joining heavy wall pipe, inspection, and how you can help your end users. Let's start with the why. In general, the fusible plastic market is continuing to expand with new users. We're getting more questions about fusion processes and visual appearance across the board. We're especially getting calls related to heavy wall fusion. Heavier walls are becoming more and more prevalent. Just 10 years ago, how many of you on this call would have thought that the 20-inch size of pipe, the DR9, would become the oil field standard size? What about DR7? For perspective, with a 20-inch or 500 millimeter pipe size, the wall thickness for a DR11 is 1.8 inches thick, or roughly 46 millimeters. For DR9, jumps up to 2.2 inches, or 57 millimeters. And for a DR7, we're all the way up to 2.85 inches, or 73 millimeters thick. So those heavier and heavier walls, even in smaller diameters, are giving us much larger surface areas. Since there's no industry definition of heavy wall, for today's discussion, I'm going to focus on wall thickness equal to or greater than 2 inches or 51 millimeters. So what's driving these thicker walls? First, higher pressures mean heavier wall thicknesses. Next, larger diameters also mean heavier wall thicknesses or heavier walls, even in lighter DRs. For example, a DR21 in a 63-inch or 1600 millimeter pipe is still 3 inches thick, almost 75 millimeters thick. Along with the larger diameters, there are newer markets and new users that have little experience with HDPE. We at McElroy take a lot of calls about fusion, and over the last few years, a lot more of those have been focused on larger diameter and heavier wall pipe. The standard procedures that are out there around the globe work for all pipe sizes, but there are some things you have to be aware of. Visual inspection can be a huge factor. How many of you, regardless of pipe size, have gotten questions about the perfect double rollback bead based on the PPI TR33? This picture is both one of the greatest tools that ever came to the industry and perhaps one of its greatest curses. It's a beautiful representation of the artistic potential of a bead, but we all know it doesn't exist in the wild. New users, however, do not know this. We need to be able to educate them on the process of fusion and how to interpret the results, especially those visual results. There are several projects ongoing to update the visual appearances in ASTM F2620. And additionally, there are multiple projects in works to address specifically heavy wall pipe fusion visual appearance. So today I'm going to talk to you about general best practices we see in the industry. The first of which, and maybe the most important, is know your customer. Do they have HDPE experience? If not, you need to get involved deeply to educate and train. Next, if there are concerns or questions from those customers, who is the decision maker on that project? You need to be able to speak the language of the decision maker. In other words, know your customer. If it is an engineer, focus on information, standards, basis, presentations, not unlike this one that I'm giving today. You can call in a 100-mile expert. There's always an opportunity to get someone outside of the specific project to help and give a good explanation or professional opinion. We at McElroy are always willing to help. Don't ever hesitate to call one of us here at McElroy. So let's talk about some of the tools that are out there now to help you. First up is PPI Technical Note 51. Polyethylene pipe butt fusion structure, process, and terminology. This document covers butt fusion structure, how it forms, the whole process, and much of the terminology that you used. Most importantly, there is a picture in there, and this is the only one that I know of today in print, that includes this picture, and it shows a quote-unquote typical heavy wall bead. Note that it does not look like the TR33 single rollback bead. Importantly, it identifies the potential differences of the presence of the heat soak bead and the actual fusion bead. To explain this further, let's go through the mechanics of what can actually happen during a heavy wall fusion. As we bring the pipe in contact with the heater plate, we see that the heat soak begins and the molten material begins to flow out. This forms our initial bead up. Remember that we're soaking here at 4.5 minutes per inch of wall thickness. That bead is exposed to the air and has the ability to begin cooling and skinning over. Next, when we open the carriage, pull the heater out, and that heat soak time, the minimum bead have been achieved, that material is removed and the molten ends are brought back together, pushing that molten material bead out of the joint to make the actual fusion. That initial bead from the bead up has had time to form a skin may now retain that shape, resulting in a configuration that looks somewhat like this. For some of you, you may recognize this double rollback bead as an indication of heating under pressure. It's important to understand the mechanics of this process, why this bead appears like this, and how to address it. Best scenario is to have a data logger. Use it as a backup to show that the process was correctly followed, that a cold fusion did not occur, and that you're able to explain the mechanics of the formation of these beads. Now, that was a little bit like the TR33, the potential perfect bead. Let's look at some potentials that are also out there. There will be lots of different types of forms that can come based on ambient conditions like wind and temperature, heat soak times, pipe resin, manufacturer. In this case, we have two distinct beads with the initial rollback bead being above the surface, hanging out here in the air. Also note that the internal bead can be very exaggerated. That internal bead is not considered in any of the existing world standards, but we do get calls about people looking at that bead inside the pipe, especially if the pipe's big enough for them to walk into and see that bead. This is another area where it's an opportunity for you to know your customer and educate them. Another bead scenario is two distinct beads with rollback to the pipe surface. You see that initial bead form here that has rolled back to the surface. From the outside, this could appear as a double waved bead. You're looking at those surfaces and seeing that double wave. Now here's a real world example. In this cross section, we see two distinct beads, but from the OD of the pipe, this could appear as a very large bead or a double wave. Some of you will also note a little bit of mismatch here in this pipe, but it's well within the tolerance of the F2620 standard. Some other real world examples of large diameter or thick wall beads would be here. Visual inspection is a good tool, but it's not the best tool. It's not always the best tool. Regardless, you need to understand how these form. For example, in this case, this picture shows a joint with two distinctly different beads. Now, ASTM F2620 says it's acceptable to have non-uniform beads that are uniform around the circumference of the pipe. So this bead on this side can look different from the bead on this side as long as they are uniform all the way around the pipe. This joint was data logged and showed that the procedure was followed to the letter. One other component of the visual inspection criteria you need to understand is this call out in ASTM F2620. It's important to note that this is to prevent the initiation of a crack in the joint, that the V-groove depth does not go deeper than half of the bead height. Now, specifically in this call out, you'll see that the picture shows that the V-groove actually goes below the surface of the pipe. And that's really what we're trying to avoid. However, the call out says The V groove should not be deeper than half the bead height. What is important with heavy wall fusion is to understand where and how to actually measure your bead height. In this particular case, remember our picture with a fusion bead held up by the initials heat soak bead. Traditionally, the measurement for this would be at the highest point on the bead, shown here by the green arrow, to the deepest point on the V, shown here by the red arrow. For this bead, that red arrow is just over half of the bead height in this measurement. Now, because we're looking at this in cross-section, we can see that in reality, the actual bead height is really this thin section of this bead shown in blue. Now, it's also held up by this the initial bead that's out here in the section. So what happens if we look at that section? And what I'm going to do is I'm going to throw up a crude drawing and show this in a little bit different format. So if we say, let's ignore this outer bead and focus on the actual fusion bead, you'll see that that bead is actually held up in the air. If I throw on a quick overlay of that bead, we still see that the V group is greater than half the height. However, if those beads weren't held up in the air by the melt soak bead, if we rotated those down, what you'll see is that the V groove depth is not deeper than half the height, shown in red. Now, this is only seen in that cross section. You may have to help educate your end user and use a destructive test sample to explain this and show that fact. So we've talked about the visual aspects of the fusions. Now let's get into the procedural side itself. Now we're going to run through some best practices for alignment, for using the data logger, temperature assessment, pressure use, and finally testing. First, heavy wall pipes can have a variation in the wall thickness due to the way that they're made. Even low sag or low slump resins can have large variations in the pipe wall, just simply because of gravity and the speed at which the pipe is extruded. Aligning these variations is very important. You want to make sure that you don't have differences in that process so that you end up with a mismatch of the thick piece on the top side connecting to a thin piece on the top side. An actual picture of this would be shown here. We see two different wall thicknesses. You can see significant wall mismatch on the ID of the pipe. The OD is going to always align, but if you have a very thick section that's aligning with a thin section, your ID can have a pretty significant mismatch. And we want to avoid that. So best practice for any pipe size is to align the print lines and align them in the same direction. This aligns that pipe in the same configuration as it was extruded, minimizing that mismatch. So if you keep those aligned, keep that print line in the same direction, keep that printing in the same direction, you will align that high-low mismatch that can be there. Now, you of course know that I'm going to talk about the data logger. It provides you with a huge value proposition on any job. This is especially true with heavy wall pipe. It gives you input on all of your parameters, the operator, the equipment, the pipe procedure, everything that goes into it. It includes built-in calculations to eliminate the need for hand calculations or transposition errors. It validates your procedure. Remember that double wave bead? Again, our traditional look at that visual inspection is a double wave bead indicates heating under pressure. With this, you can validate that that is not the cause of it, and then you can talk about the actual formation of heavy wall pipe. You show that that procedure was followed correctly. You include photo validation, pictures of the joint, pictures of the fusion procedure, pictures of the process, cleanliness, cleaning of the pipe, visual inspection. Document the bead itself throughout. It also gives you GPS and GIS tracking, giving you full traceability of that project. So again, industry best practice, it gives you that background, that backup, and validity, especially with a new user. So let's talk about the allowable temperature range for heavy wall fusion. The allowable range today is really pretty large. For ASTM F2620, it's 400 to 450 degrees Fahrenheit. In ISO 21307, you're at 215 plus or minus 15 degrees Celsius. But heavy walls take a lot of heat. There's a lot of surface area, and they absorb a lot of energy from the heater. So best practice is, and we traditionally train in this, is that we train at the middle of the range. So 400 to 450, middle of the range is 425, and 215 plus or minus 15, the middle of that range is 215. So best practice in general terms is to run the heater to the highest end of that allowable range so that the pipe doesn't pull all the energy out of the heater and keeps the heater in the allowable range. Industry best practice for this area is to run 440 to 450 on the high end of that heater range. For ISO 21307, you want to run in that 225 to 230 C range. So again, higher temperature gives you the ability to maintain that temperature, make sure there's not a lot of heat pulled out of the heater on the initial contact, and then you're maintaining that temperature in that range. So let's look at the pressure ranges themselves. Let's talk about interfacial pressure. First, F2620 allows 60 to 90 PSI. While ISO is a very similar range with 0.52 plus or minus 0.1 megapascals. The same thing here, traditional training is to be in the middle of that range. F2620 is right at 75 PSI, traditionally trained, and ISO at 0.52 megapascals. The industry standard best practice here is to set your equipment to use the lower end of this interfacial pressure range. For F2620, instead of running at 75 PSI, best practice has been to run 60 to 70 PSI. So 65 plus or minus 5. Same goes for the ISO single high pressure procedure. Run in the range of 0.42 to 0.48 megapascals. Now, every time I've had this discussion or people ask about this, someone always asks if lower is better, why not use the low force standards? And the simple answer there is, remember that both ASTM F2620 and the ISO single high pressure 21307 have a range of high pressure values. There are a number of advantages to the high force, including shorter cool times. The other advantage has been shown to help push contamination, if it's present, out of the fusion zone. This is true across the entire high pressure range, that entire 60 to 90 pressure range. For the low force standards, that is not true. You do not get a full push out of material across that fusion joint. It's also why you have a longer cooling time there. So there's lots of advantage to remaining in that high pressure range, and it's simply here to run in the lower end of that cycle. Now, let's talk about testing. The traditional bend back test in F2620 is to cut a 1-inch strap longitudinally out of the pipe and bend it back on itself. There is a note, however, in ASTM F2620 that says this is only valid up to 1-inch wall thickness. So what do we do for heavy wall situations? Well, there have been some pretty creative people out there over the years. Now, this method is creative, but it's not safe. Please don't do this. If you can imagine where that piece is going to go if it springs out. Now, other solutions we've seen in the field include this one. This is also very creative, but it's not safe. In fact, this isn't just a one-person job. This is actually a two-man job. Now, it takes two to this. Now, imagine what happens if just one of these brave souls lets go or falls. What's going to happen to that bar? There is a better way. Enter the guided side bend tester. This tool allows you to easily test in the field 1-inch through 7-inch wall pipe. So 1 through 7-inch wall pipe. The test is also backed by ASTM standard F3183. It's the standard practice for guided side bend evaluation of polyethylene pipe butt fusion joints. It gives a repeatable standard for testing butt fusion joints up to 7 inches or 178 millimeter wall thickness. It gives examples of pass-fail criteria, including both ductile and non-ductile failures. And maybe most important is that it is included in the upcoming revision to ASTM F2620. We expect that to publish really by the end of this year, so it should come out by the end of 2020. In addition to the guided side bend test, there's also the in-field tensile tester. In-field tensile tester provides test capability for wall thicknesses up to 5 inches thick. Like the guided side bend test, this is a qualitative measure and gives you the ability to test and validate in the field without long downtimes waiting for laboratory results. Now, we've gone through quite a bit today. Let's go back and recap. Best practices you should practice. First, educate yourself and your users. Know your customer, know what they need, understand what they need, and be able to talk to them and explain to them. Know your materials, know how these processes happen, what is different about the things that you're using, how material functions. Visual inspection criteria. Again, this is one that has a lot of work to be done in the standards world, but we need to help educate people on visual inspection, especially related to the mechanics of these heavy wall pipes, how it happens, what happens, and give them really help to satisfy that user on why the materials look the way they do. And know your resources that are available to you, whether it is consultants that are in the industry, whether you want to call on McElroy, whether you use presentations like this presentation here, other presentations that are available to you, the Plastic Pipe Institute, the Alliance for PE Pipe. Rely on resources so that you have the ability to talk through those pieces. Use a data logger. What better backup could you have for pictures, standards, proof of the procedure that was followed correctly, all of the pieces that are there that give you the ability to show that the process was done correctly. Satisfy that user, whether they're a new user or an experienced user. Data logger and data logger vault data give you that capability to back up that information, back up your claims. On the temperature side, you want to run in the higher end of the range. Remember, think about this when you're pulling heat out with larger surface areas. So run at the higher end of the range, get that heater heated up there to the top end of that range, and that way that it'll stay stable throughout the process. On the pressure side, run at the lower end of the range. Gives you a lot of headroom for whatever you need in terms of pressure that you need, but if you run in that lower end of the range, you're going to have a better process. Now, any one of these, they will run, the joint that you make will be fine. All of these processes work correctly. These are best practices. On the test side, look to the guided side bend tester. Give your users that ability to have tests and in-field validation for these heavy wall pipes on site without any downtime. In-field tensile tester gives you that, again, that ability to validate safely and with confidence.
Welcome, Jim.
All right, good afternoon, Dave.
I know this is always the best part of your job. I know calling you from all places in the world saying, hey, Jim, you got to look at this joint. Can you give me a little bit
That's right.
perspective on that? So I'm always appreciative when you're on the other end of the phone helping a little CSI, if you will, of bead geometry. So
It's always fun, too.
yes, it is. Yes, it is. Okay. So we've got some questions here for you.
All right.
Let me start with, can a bead look perfect and yet still be bad?
Yes. Yes, it can. And bad is a relative term. It's hard to do that. Again, the polyethylene is such a forgiving material. It's really hard to make a quote unquote bad joint. It really is. But that's where data logging, following your procedures, following your steps can really be a part of this. Some of the people on this call, for example, will know that in the natural gas industry, people are very focused on that perfect double rollback bead.
Right.
There are ways that you can make that perfect double rollback bead, but you aren't going to follow the procedure. So some of these modern materials won't give you that perfect rollback bead. You can make it happen, heating longer, or forcing under pressure, doing some things to cheat it to get that bead, but you're not going to follow the procedure. So I would say let me change that question a little bit and say, are there ways to get a really good looking bead without following procedure? Yes, but the core here is that making the joint to the procedure really, we know that the procedure works. When you don't follow that procedure, you're throwing in a variable that may or may not have long-term effects. And we just want to make sure that long-term effect
So I maybe kind of paraphrase here. If given the opportunity, you'd suggest somebody follow the procedure and let the bead fall as the bead may, and not try to create a bead that someone's looking for.
Exactly. That bead has always been an indication, and for a long time it was the best indication we had. Today it's still an indicator. It's not necessarily the best indicator. Following the procedure, having a data logger record showing that you follow the procedure, trained operators, good equipment, all of those pieces really are the more important stages of this, because as the material changes, so does the resulting bead.
So it's kind of like materials. It's kind of like bad weather. When you look out and there's big, huge thunder-looking clouds, it tells you one thing, but you'd rather have a radar showing you exactly what you need and listen to an expert.
Exactly.
I get that analogy. What are some of the destructive methods that you like, and what are some that maybe you don't like?
The destructive methods, is that?
Yeah, the destructive methods.
For 1 inch and thinner, that the side bend test, or the bend back test is a really good test. All of those short-term destructive tests are short-term destructive tests. I really like the guided side bend test. It gives you some good manageable ability to deal with really heavy walls. And I showed some of those pictures in that slideshow. People get really creative, but unfortunately there's some crazily dangerous ways people go about bending those big pieces in half. And with a fairly easy piece of equipment, just go to Home Depot or Lowe's or whatever your local hardware store is and get a planer. You can do that. You can do that sample real easily and quickly. You can do it for thinner walls than 1 inch. It's just that height to width ratio that gets kind of challenging with a planer, but it can still be done there, even with that. So at the top of the list, I think that one's my favorite.
The guided side bend tester, infield tensile tester.
Infield tensile tester, you got the just standard bend back if you're doing 1 inch or less. Yeah.
So I asked which ones you like. Are you willing to go out on a limb and say which ones you don't like?
I don't know that there's any that I don't like, or any that I have seen that are problematic. The ones that I think are
I don't like is when somebody calls and says, I want to establish a number based on this qualitative test. You know, so what was the pressure when I bent this piece? That doesn't matter. It's a qualitative test. We're looking at, was that joint strong enough to hold together under that extreme stress?
Got it.
And that's more of an understanding of the process than
Okay. And
good question.
are there any non-destructive tests that you're keeping your eye on?
Yeah, you know, there are advancements in the ultrasonic and microwave testing that's out there. For those of you that didn't know, McElroy had an ultrasonic testing piece of equipment in the early 90s, and it's a little bit of the holy grail. I think it's a great idea. One of the challenges we have is that there's really not many failures in butt fusion. And when we do see them, they're from gross mistakes that are picked up by the data logger or that visual inspection.
So looking for a problem where there is none, huh?
Yeah. It still takes a technician to analyze the results, and there's not acceptance criteria. So as that technology continues, there are areas where it's used in the nuclear industry, for example. And for those that are in the nuclear industry, it's probably not a bad thing that there is a no acceptance criteria, because we want it to be, if it's not absolutely 100%, we probably don't want to go into a nuclear power plant, even for the fire safety.
Yeah. Okay. Here's one from the audience here. When I get a picky inspector and I haven't picked the mid-range of the parameters, how do I get them over that hump?
You know, first, I'll go back to Eric Maddox. Empathetic listening, building trust. Talk to them about what that is. It's a range of variables that are allowed, and I'm going to keep coming back to a data logger. Show the data. If you're on the low end of the range, then allow that low end of the range, and you show that you have that data. I didn't include it in this presentation, but a lot of people on this call have seen me do a presentation around how the standards were developed. This standard is a window inside of a window inside of a window. So let's pick on the temperatures. That 400 to 450 degree range, if I'm at 399, that doesn't mean the joint's going to fail. That 400 is actually above the testing range that was tested. So it was tested down into the 300, 350, 375, 375 range. So it's a window inside of a window. So first, it's really just knowing the standards, where they come from, helping educate those people. After that, I would say call in a 100-mile expert. There's a lot of folks that are out there that are retired from the industry or are doing consulting in the industry. We're always happy. I'm always happy to answer the phone. That 100-mile expert goes a long way sometimes. So feel free to reach out to us if we can help. Sometimes it's just simple education. Hey, that 400 to 450, the original testing in TR33 was done at 355 to 510 degrees. So,
right.
You know, there's some ranges, there's some ways to do that. Start on the very front end, build that rapport with that inspector. But sometimes you've got to call in a 100-mile expert, somebody that's not you.
Yeah, my experience is that has been helpful, but I like that empathetic learning or empathetic listening and trying to understand what their problem is and how to do that. So there's a question here. This is my area places a requirement for the bead to meet certain height and width parameters. Do you think that's a good method?
It was at one time. Uh, and most of those come from the original version of TR33. There's a picture in TR33 that has a dimensional ratio of the height of the bead to the width of the bead. And that can be done. It's even, there's times when it's not even appropriate for medium density pipe, but it really came from that medium density world and doesn't take into account the high density world. And that's why ASTM F2620 doesn't have that ratio in it anymore. Because today's modern materials, the 4710s, the bimodals, even the medium density bimodals, flow differently, and that bead configuration is different. And that's where F2620 really is our basis for that inspection, to say that it doesn't even have to be the same bead size side to side,
Right.
as long as it's consistent around the pipe. So we still hear pockets of that exist. Some of that is just pure, it's been that way for a long time. Another great example from Tim Bosch this morning of we've always done it that way.
Right.
And the world has changed, the resins have changed, the world has changed.
Yeah.
And that's where sometimes you got to call in and get some help.
The four-cornered ham is a perfect example of that, right?
Exactly. That is a four-cornered ham.
Cut the corners off the ham. It's only until you get back far enough you realize why, and then whether or not was a good decision or not. So
that's exactly right.
yeah. So let's say I'm out in the field, and I get presented a joint and the bead looks strange to me, and the person didn't data log. What do you do?
Well, there's a couple of things you can do. You can, interview the person that did the joint, find out how they did it, have them make another joint with that same material and following the same procedure and see if you get the same results. Often what we do is we get a lot of calls that come in and say, hey, even we did data log this joint, but it was data logged different than we expected. The procedure they followed was different than we expected. Can you help us decide if this is going to be a good joint or not? The simple answer is you're going to have to test it. One way to do that is to take that same material and destructively test it. So make another joint following exactly what you did in this case and do one of those destructive tests and satisfy yourself on the job site, because with every variable, there could be something that comes into play there. But if you do that, you can satisfy yourself that the joint that you made is good. Again, this is an incredibly forgiving material. You think about the global pipe standards that are out there. There are pipe standards that run all the way from 14 psi up to 120 psi capability. So, it's an amazingly forgiving material. But when you don't follow that procedure, you've got to be able to reproduce it and see whether that works or not.
Got it. Okay. You mentioned changes to F2620 to address the inspection issue. Can you tell us anything about what those changes will look like?
So today in F2620, there's a lot in there that is around what is a good joint. The problem with what is a good joint is that there are a million ways that a joint can visually inspected look good or still be an acceptable joint. In terms of a poorly made joint, there's only so many ways that it can be made that are visually indicating that it's a bad joint. So much of what we're doing is taking that primary bead picture that says here's what some configurations of a bead that are good look like. Getting rid of all of the other kinds of good inspections, or not getting rid of them, but minimizing those and showing here are the few ways that it can be a grossly incorrect joint.
So really trying to,
focusing on those.
it's said differently, it's easier to point out the few things that will make a bad joint than the 100 things that will make a good joint. Yeah.
Yeah, and at one point, there was even talk about putting together a catalog of all the possible good joints. Well, it would be infinite, and we all know that there's an inspector out there that would go through 1,000 pictures and say, well, this one doesn't look exactly like any one of those 1,000.
Right. What would you say some of those, what are the most common ones that you see out there that create a bad joint?
So visual contamination, when you can see something, whether it's a chip hanging out of the joint, I mean, that's kind of the most gross version of that. You see something dangling out of the joint. Or with the high force fusion procedure, you actually can see contaminants. So if there were dirt that were contaminating that face of that surface, you're going to see it at the bead and at the exterior of the joint. And so that's a good indicator there. The other gross visualizations are really mitered joints where their face-offs weren't good, or let's say that you have a face-off that actually physically have a gap present, that you didn't get a complete face-off. So most of those that are visual are truly what we call the gross representations, as they are the extreme end of it.
And can you see a heat under pressure in a bead?
You can, but again, as I talked in here, one of the things we're seeing in that thicker wall pipe is that in traditional history, heat under pressure can be seen as that double wave.
Right.
But with more and more molded fittings, you definitely see molded fittings can have a double wave in them. That thicker wall pipe can have a double wave in them. So you really have to take into account the material that you're working with when you're looking at that and see that double wave. It is not as direct a indication as it has been 15, 20 years ago with medium density pipes.
But I'm guessing that if you see a double wave in any size and you don't have the data logger, your antenna gets up pretty fast.
It does. I mean, it starts asking a lot of questions. You start down the chart. Depending on if it's a picture that's been sent to me, is one side of this a fitting? Is this heavy wall pipe? What's the resin? Is this 4710? Is it bimodal? What's the material? What was the temperature of the day? Those kinds of things. So it should, if nothing else, start you down a flow chart of asking some questions.
Got it. And
was it data log? Should be the top.
Yeah. So if you data log, I mean, that's the start of it, right? If you data log it and you follow procedure, and you can take out the mitered, and you can take out the contamination, and you can take out those things, then you're pretty well down the path of knowing that you've done everything in your power to get a good joint, right?
That's right. And pictures play a part in that too. Make sure that, you want to make sure that face-off was done correctly. If there was no contamination in there, a good picture of the bead shows you a lot of that information. So all those pieces come together to give you a history and a documentation of the joint to show that it was done correctly.
Okay, so one final question. It's more of a curiosity that wasn't asked by the crowd, but by me. And the picture of the yellowish orange pipe that had a kind of unique bead on one side, that wasn't even on both sides. Can you?
Yep.
Did you prove it? And if so, why?
Actually, I was on that job site, and yes, I did approve that bead.
I approved this message.
And I approve this message. Uh, and I'm going to pop that picture up on the screen actually right here. So in this particular case, this was a joint that was going down a hill. So we had different forces acting on both sides of this pipe. And so aware of that, knew that going into this, looking at that joint, and helped them kind of look at this and take a good look at this. The data log on this joint looks very good. In fact, this particular job, they actually cooled significantly longer than required. It was just something that the engineers felt like they wanted done. But in this case, this was driven by the fact that this was on a pretty steep incline.
Okay, we got some more questions coming here. So, I said I lied to you about the last question. So this one is: does the cooling cycle length change the final bead appearance, and when should inspection happen?
No, the cooling cycle length doesn't change it. That bead is pretty much formed within seconds of the contact of the pipe that's coming together. If I didn't have, again, another one that I don't have in this slide deck, but the cooling cycle, both internal to the pipe, you start from that molten phase and it drops really, really fast down to the point of co-crystallization. And that's where that joint's really pretty much stopped moving, or where that bead's moving. And with it exposed to the air with all the other things, that's pretty much done. So in terms of inspection, you can really start looking at that inspection just as soon as you have access to the machine. Sometimes that's a little difficult depending on the size of the machine, the location, lighting, etc. If it's in between those two jaws, until you open up those jaws.
Let me ask that question slightly different. If you're doing a destructive test, how long should you let that joint cool?
So all of the destructive tests, and this is all of them across the board that I'm aware of, require that joint be cooled down to ambient temperature. The old joke is it could be up. It depends on the thickness of the material. It could be up to 2 to 3 hours. I believe I'll have to go look. I believe there's a couple that even allow you to, once the sample is pulled out, for it to be cooled in a water bath to bring that down. But you're essentially trying to test this at a in situ, in place temperature. If you try and test it when that bead is still hot or that joint's still hot, you're really not getting the test of what it's going to be when it's
right. I remember from your optimized cooling, you had that pretty rapid drop, but then it's got a long tail before it ever gets to. Yeah, I think Ted Strickland did a paper for plastic pipes, I don't know, maybe 10 years ago, that just shows
plastic pipes 13.
Yeah, how long that was. So that's pretty important. Okay. What post-installation practices do you recommend? Hydro test, etc.
This is my personal bias. I prefer the hydro test. There are some folks that are using pneumatic testing. Pneumatic testing is a viable test out there. There's an ASTM standard for it, but it's I hate to say dangerous. It is you need to be very, very safety conscious when doing those tests. It's typically a very low pressure test, but a pneumatic test, uncontrolled, can be a pretty violent exposure to a system. So the hydro test is a good test. It is not a 100% test for a hydro system, but it is a very good test.
I assume on the pneumatic side, that's why the pipe companies, when they're doing their testing, and they're taking something to failure, they do it underneath the water. Is that correct?
Yeah, even a 4-inch pipe inside a pretty good pool, when it explodes, is kind of a Hollywood explosion
Yeah.
in the pool. And I've heard stories of large pipes being blown completely out of the ground in a 6 or 8 foot burial.
Wow. Well, it always amazes me how much time and effort we spend on this, to how few, joint failures we
Yeah.
have. But I just think it kind of goes to the nature of our upbringing, the nature of inspectors. So I think what I hear from you is data log it, follow the procedure, get good pipe, and you're going to live a stress-free life.
That's right. Right. And to your point, I think the other thing that we've done is we've established that polyethylene is no failure is acceptable. And that's really a good thing for us. And for as few as we have out there, it's pretty spectacular, but we can avoid any of them and continue this leak-free system. That's the spectacular part. The only other piece I'd add to your piece of data log, document, use good material, good equipment, and good operators is know who your resources are. McElroy is always going to be a resource. Please don't ever hesitate to call one of us here. A lot of you call me or Mike Pacheco or Dave. Don't hesitate to call us. We're happy to help. If we can't help, there's other folks that we can help get you in touch with. So know your resources, and there's a lot of things we can do to help on that front, especially at the engineering level. The engineer, we talk to an engineer, explain these pieces to them. It really smooths the process quickly.
Well, Jim, thank you. Thanks for I always learn so much from you. That's why I enjoy working with you.
Well, thanks, Dave. I appreciate your time and help.
I'm sure everybody had a great time. Tune in. We got more great presentations ahead.